In this section, we'll be taking a look at the multicast concepts objective of the JNCIP SP exam. We'll cover a basic overview of multicast. We'll take a detailed look at PIM, including dense mode, sparse mode, rendezvous point resiliency, and source-specific multicast. We'll also finish by taking a look at RPF. For more detailed coverage of this topic, please check out the Juniper courses AJSPR, JL2V, and JL3V.
In this video, we're going to take a high-level look at multicast. So first and foremost, what is multicast? Well, if you think about just standard unicast traffic first off, we're talking about getting traffic from one specific host to another specific host. With multicast, as the name would suggest, we're getting traffic from one specific host, a source, to multiple other hosts. In this case, the terminology we use is receiver, and we have receivers illustrated on the board with R. And when we're sending multicast traffic, the source address is a standard IPv4 address. The destination address is an address within the 224/4 block. And instead of referring to this as a destination IP address now, we refer to it as a group address. And to facilitate this communication from one source to multiple receivers, we have a suite of multicast routing protocols. The purpose of these multicast routing protocols is to build a forwarding tree between these receivers and the source of the traffic. What we're doing is we're trying to indicate from the receivers up through the network to the source that we are interested in the traffic. And the end result is that we build this forwarding tree. The forwarding tree on this diagram is illustrated in orange, routing from the source to the receivers. So we have traffic going from one source to multiple destinations, multiple different receivers. So what routing protocols do we use in this scenario? So if we start off at the receiver end, we have Internet Group Management Protocol, or IGMP. Now this operates between the receiving hosts and the router to which they're immediately connected. And receivers illustrate their desire to join a group to the firstmost upstream router using IGMP. Then routing within an autonomous system, we can use one of two routing protocols. Pretty much we're using one routing protocol, and this is PIM, that's Protocol Independent Multicast. There is another routing protocol called Distance Vector Multicast Routing Protocol. However, this is largely deprecated. So in subsequent videos, we're only going to be focusing on PIM. If you're running a multicast network, this is going to be pretty much the only routing protocol within your network that you're configuring. There is also a interdomain routing protocol that's used in conjunction with PIM in certain scenarios, mainly when you're dealing with any sourced multicast, which we'll talk a little bit about in a future video, and that is MSDP. This is Multicast Source Discovery Protocol, and it's a way to tell bordering autonomous systems about sources of multicast traffic that you have within your network. Now we've talked about some of the aspects of routing for multicast. What kind of applications typically would use multicast? Well, there are two main ones that are in significant use out in the industry today. The first is the distribution of IPTV broadcast, and this can either be to set-top boxes as the receivers, or it can be to intermediate points within a broadcast infrastructure. And the second is over stock exchanges, the distribution of stock telemetry information. Multicast lends itself to a very equitable system. So you can have the exchange broadcasting the price of various different elements, and all interested parties can be listening to that and receiving the same telemetry at the same time. So that was a quick overview of multicast use cases and key multicast components. In subsequent videos, we'll delve into these components in a little bit more detail. So we've talked about some general aspects of multicast. In this video and subsequent videos, we're going to talk about PIM specifically and how we use it to build multicast trees within a network. And we're going to take a look at the various different flavors of PIM, these of which are outlined on the left-hand side of the board. We'll first focus on any sourced multicast. So that's building trees when traffic directed to a group can be from any source. And there are a few flavors of PIM that operate for any source multicast. We have dense mode, sparse mode, and sparse dense mode. And then we'll also take a look at source-specific multicast, or SSM. And so this is where we are joining a specific source for a specific group. In this video specifically, we're going to take a look at dense mode PIM. And this is probably the easiest mode of PIM to understand. That's why it's a good place to start. So say we have this topology on the board here. We have a source connected to a designated router, and we have a receiver at the bottom. We have three routers here, and they're all speaking PIM dense mode to each other. So what happens? So say the source starts sending multicast to a given group. That traffic arrives on the designated router. In dense mode PIM, we're going to be flooding traffic out of all downstream interfaces initially. So traffic from the designated router lands on these two downstream routers. And from this router here, it's delivered to the receiver. So you can quickly see how traffic is delivered to all routers in the network and all potential receivers connected in the network. However, there are going to be some routers in the network that are not connected to any receivers, such as this example here. And we obviously don't want to be sending traffic to these devices unnecessarily, because that's consuming resources in the network unnecessarily. So when a router operating in PIM dense mode doesn't have any receivers connected, he sends prune messages upstream, and that has the effect of stopping the multicast tree reaching that device. Thereby traffic is no longer delivered to that device. If in the future a receiver were to connect to this device, he could rejoin the tree by sending a graphed message upstream, and then traffic will then be redelivered to him, and he can onward deliver it to that newly connected receiver. Now imagine we have PIM dense mode deployed in a very large network. The initial state that we have in PIM dense mode is that we're sending traffic to all devices. And this could potentially be needlessly consuming a large amount of resources on your network before we get to the point where prune messages are propagated and we strip the tree down. So this unnecessary use of resources means that PIM dense mode is fairly infrequently used in networks in live environments. Instead, you tend to find that sparse mode PIM is much more widely deployed. And we'll take a look at sparse mode PIM in the next video. In this video, we're going to talk about sparse mode any source multicast PIM. Because we're talking about any source multicast, the receiver is interested in receiving traffic for a given group he doesn't mind what source is providing that traffic to that group. He also doesn't necessarily know where that source is located. So in sparse mode PIM, we introduce a new device, a device called a rendezvous point. And this rendezvous point is basically doing as its name suggests. It's providing a meeting point for receivers and sources to discover each other. So how does sparse mode PIM operate? Well, the full flow of sparse mode PIM is fairly complex, fairly involved. But for the purposes of passing the JNCIP service provider exam, this video should just give you a quick overview, a quick refresh of the various different components within this. But this video is certainly not going to cover every aspect of sparse mode PIM operation. But let's just see in high-level overview what happens. So say we have a receiver and he's interested in receiving traffic for a given group. What he does is he first sends a join message to the rendezvous point, to the meeting point in the network. He doesn't mind where the traffic is going to be coming from that's going to be delivered to this group. So he sends what's called a star, G join. So any source to a given group, he's interested in traffic. So he sends that join message to the rendezvous point. And if this is bubbling up all the way through the network, the net effect being is that we build what's called a rendezvous point tree. So this is a shared tree where receivers are building a path to the rendezvous point to receive traffic for this given group. So this is routing signaling from the receiver to the rendezvous point. Say now a source starts sending traffic to the network to that group. The traffic hits the designated router, the first hop router in the PIM part of the network. This triggers a register message. So this is a PIM register message that encapsulates this multicast traffic, and this is sent to the rendezvous point. This triggers the rendezvous point to send a specific join up to the designated router. And this join means that the rendezvous point joins a shortest path tree to the source, so he can start to receive traffic from the source and it can be delivered to the rendezvous point. At the rendezvous point now delivers traffic to this group over the rendezvous point tree, the RPT, to the device that's connected to the interested receiver. And now the interested receiver is receiving this traffic. So you think this is all well and good, but there is more to go on here. The rendezvous point tree is perhaps not the most efficient path through the network to the source. So as soon as the downstream most router receives traffic on the rendezvous point tree, he is now able to see where the source is for this given group. So what he does is he signals upstream a S, G join. So that's a join for the specific source that's sending traffic to this group. And this S, G join bubbles up through the network until it hits the designated router, and we join the tree that's routed at the source. And this then forms the shortest path tree from the receiver to the source. So this is the most optimal path from the receiver to the source. At this point, the last hop router here can send a leave message to the rendezvous point so that he leaves the rendezvous point tree so that we're not sending duplicated traffic through the network. At this point, we should also mention sparse dense mode PIM. And this is basically just operating a network where you are supporting both dense mode and sparse mode PIM, and you're doing this on a per group basis. So in this video, we covered sparse mode and sparse dense mode PIM in a any source multicast environment. So with sparse mode PIM deployed in our network, we need to think about resiliency. The entire operation of PIM sparse mode is dependent on this rendezvous point device located within our network. And for resiliency purposes, obviously we need more than one rendezvous point. And there are a number of different techniques that we can use to facilitate the use of multiple rendezvous points within a PIM sparse mode network. The first is that we can use supporting bootstrap routers. The second is that we can use a technique called auto-RP. And the third, perhaps the most widely used option, is to use a technique called Anycast RP, Anycast rendezvous point. And this technique warrants a little bit of further discussion. So with Anycast RP, what we do is that we configure multiple rendezvous points within the network with the same IP address. So devices connected to receivers route to this IP address. They have this IP address statically configured within their PIM configuration. And they hit one of the many rendezvous points that are configured in the network. And then from that rendezvous point, the same signaling mechanisms take place as we've described earlier to get to the source. So you can see with this that we have different state available on different rendezvous points depending on where they're positioned in the network. So we need to synchronize the state on these different rendezvous points. So to do this, we turn to MSDP, Multicast Sourced Discovery Protocol, and we run MSDP between all of the rendezvous points. And what MSDP is doing is it's propagating all of the S, G state, the binding of that source IP address to a group address. It's propagating all of that state between all of the rendezvous points. So this way, it doesn't matter which rendezvous point you land on, you're going to get access to the same forwarding state. So that's how you provide resiliency in a PIM sparse mode environment. And finally, we'll take a look at source-specific multicast. So source-specific multicast removes a significant amount of the complexity that you find in sparse mode PIM. And we do this basically because we're saying to the network that the receiver is going to know the IP address of the source. So with this simple assumption, it means that we can completely get rid of the rendezvous point and all the complexity that goes with it. So to do this, we require IGMP v3 to be running between the receivers and their connected routers. This way the receiver can signal to the connected router that not only is it interested in a specific group, but it's specifying the source that it's interested in that's going to be sending traffic to that particular group. So we have a receiver signaling to its upstream router that it's interested in a particular source sending traffic to a particular group. What then happens in the PIM speaking portion of the network is that we send S, G joins upstream going across all of the PIM speaking routers until we hit the source. And this is sufficient to build the shortest path tree, the SPT, between the source of the traffic and the receiver. And so you can see how this is a much more simplified operation than if we have to use an intermediary rendezvous point to facilitate linking that source to that receiver. Obviously, the downside is that the specific IP address of the source needs to be known ahead of time. But because of its simplicity of operation, we are seeing that more networks are starting to deploy SSN as a replacement to ASN. So remember that forwarding in a multicast network is tree-based, and in networks that have very complicated topologies, and maybe if a misconfiguration happens, there could be the possibility with these tree forwarding topologies that we start to get packet duplication and maybe even routing loops. To analyze this concept, let's walk through an example, which is what we have on the board here. This receiver has indicated its desire to join a group to its first hop connected router. This is resulting in a S-G join that bubbles up through the network to the source. And this S-G join is going to be sent to the best path to the IP address of the source. If this was a star-G join, we would again be sending that star-G join to the best path to the IP address of the rendezvous point. And when I say best path, by default what we're doing is we're looking in the inet.0 routing table, the standard unicast routing table, for the IP address of the source or the rendezvous point, and we're choosing the interface that has the best route to that IP address. And over that interface, we're sending the join message. So these messages then bubble up, the same process going on at every router, and we create the multicast forwarding tree. Say now that we have this tree structure, and for some reason, maybe a misconfiguration on this router here. This router starts sending multicast traffic for this particular group across to this router here. This router is already receiving multicast traffic over the interface from which he sent the S-G join. So we're starting to get traffic duplication on this router here, and we're potentially sending duplicate traffic down to the receiver, which is obviously undesirable. So this is where RPF comes in. And RPF prevents this situation from happening. Whenever a multicast speaking router receives a multicast packet, that device performs a IP lookup on the source IP address of that packet. Again, by default, we're using the inet.0 table. And if that packet is received over an interface that isn't the best path to that IP address, then we drop the packet. So in this case here, the source is located here, and the best path to that source is via this link in the network. So multicast packets from this source received over this interface pass the RPF check and can be onward forwarded. Multicast traffic from this source to a given group received on this interface are again subjected to an RPF check, but in this case, this interface is not the best path to the source IP address. So all of these multicast packets are dropped because they fail the RPF check. And this is how RPF operates in a multicast environment to prevent traffic duplication and traffic loops. In some situations, it might be desirable to maintain a separate forwarding topology for multicast compared to unicast. So in this case, what we need to do to be able to facilitate this is that we need to have a different table dedicated for multicast RPF checks, separate from the standard unicast inet.0 routing table. And on Juniper devices, if we were to do this, the table we would use is inet.2. And we would need to populate this table. Generally, we would take most routes from inet.0 and we would copy them across using RIB groups. But we can also populate that routing table completely separately from inet.0. If we were using BGP to do this, there is a dedicated address family that we would use to populate inet.2. So we would then have different routing topology in inet.2 that we would use for RPF checks compared to the inet.0 table that would purely be used for unicast forwarding. And in this video, we covered RPF, that's reverse path forwarding,